Now we're going to look at this with another method, which is called the randomization approach. There is our code in your demo code for this chapter, as well as a short supplemental reading from another textbook used in other sections here. Called Intro to Modern Statistics and or IMS, and that is in Moodle for you to look at. It's just a couple pages. So the randomization approach basically calculates the original observed difference between the group's proportions, which we already did. We saw that it was like 0.11. And then it combines all of the data that we have, which is in this case 400 cases, into one big pool of data. And out of that 400 cases, we already saw that 45% of them have an injury, right? I think that was 180 people have injuries. So we have this big pool of data, but we don't know now which group people were in originally. So what we're going to do is we're going to take samples of the same size, so 180 and 220, as before, and these are called replicates. And we're going to see what the proportion of injuries is in each of these sample groups in a replicate. And for each one of the replicates, we're going to calculate the difference in proportions. Okay. So the idea is that if your original difference is due to chance, the distribution of these replicates should center around the original difference. This is what we're going to get when we plot it, but let's take a minute and look through some of this R code. So here we are in R, and this is the first example, our football soccer example, that we'll do with the randomization approach. There's a second example that looks at this with a data file. So for our soccer football, we need to first replicate the data. So soccer had 92 successes out of 180 trials. So soccer success is 92 and soccer total is 180. Football had 88 successes. So football success is 88. Football total is 220. And then we're going to figure out the proportion in S, which is the successes over the total, the proportion in F for football, which is success over total. And then we're going to look at the observed difference of these two proportions, which we've already calculated by hand. Then we're going to create the combined pool of data, and 1 is a success and 0 is a failure. So for the S's, the soccer, we're going to reproduce ones up to the number of successes in soccer. And then the rest of them will be zeros. So the total number minus however many successes tells us how many zeros we're going to have. Okay. For football, we're going to reproduce ones in the number of successes we had. And then the rest of them will be zeros. So the total minus the successes will be zeros. And then we're going to just combine this into one big, huge pool by basically concatenating these two vectors that we just made. So now we have a great big pool of 400 people with, 92 plus 88, so 180 successes. So then we're going to run the randomization simulation. So we're going to set a seed at 1, 2, 3 so that we have reproducible results. We're going to run 10,000 simulations, and fake differences are going to be a numeric vector in the number of simulations. And then for 1, 2, 3, all the way up to 10,000, we're going to shuffle the pool and we're going to sample it. Okay. So then we're going to create two groups of the original size out of that big shuffled pool. And the fake soccer will be from 1 to the total number of soccer players. And then the rest of them will be fake football sample, which will be from the shuffled pool, the soccer numbers plus one. So there were 180 soccer. So this will give us a fake sample of 180 soccer players, and then it'll start at 181 and go the rest of the way to the end of the pool, and those will become the fake football players. Then we're going to calculate the fake differences between the two. And then, because these are ones and zeros, we can use this mean to do this, and then turn that into a data frame so that we have this data frame fakes. So then we've got these fake differences, and we want to compute a p-value. And what we're doing here is we're looking at whether the absolute value of any difference, because we're doing a two-tailed, so is the absolute value of any difference greater than the absolute value of the observed difference, okay? Because it can be extreme in one direction or the other. So we're counting those and taking a mean, and then we're going to turn that into a p-value statement and print that. Okay, so there's a lot happening in this code chunk in a great big long sequence. And let's go ahead and run that. Okay, and what we get in our output, you can see it sort of starts there and it's running through all of this. Okay, so, and then it gets down to, it tells us the observed difference is 0.111, and the p-value for that is 0.0332, okay? Which is pretty close to what it was when we did, we can actually, I did the prop test up here, so do the prop test. Notice this one is 0.0339. So with randomization, the p-value is really, really close. From 0.0339, it goes down just to 0.0332. So very, very close. We can also visualize what this looks like. So we're going to plot these. And we can see that our 0.1111 is actually way out here. Okay, so it's pretty much in the tail. And then if we calculate quantiles, then we're basically achieving like a confidence interval, right? From negative 0.101 to positive 0.101. Notice that the 0.111 observed difference is above the 97.5th quantile. Therefore, it is outside of the confidence interval. Okay. There's also code in here for an example with the data file. So I'm going to leave that for you to work through and see how it compares to plugging in the numbers yourself. Okay, so we did the randomization and we are plotting the replicates difference. We saw this. We get a p-value of 0.0332. And here's our 0.111 out here in the tail. So that's just what we saw in R. We got the confidence interval with the percentiles. So this interval is symmetric around zero differences. That means if there was really zero difference, this is what the confidence interval would look like. And our observed difference of 0.11 is not hugely, but it is greater than the upper bound of this interval. In other words, it's not very likely that we would get that 0.11 if there were no real differences, which is the same conclusion we reached using the formula. For the additional example, it is doing this where you have a data set, and so the first thing you need to do is get the pieces from the data, the number of successes in each group, the total number in each group, the proportion successful, etc. Then once you have those, you can just rename things and run the randomization the same way. So that code walks you through that. That's it.